Okay, so we'll start calculus 2. This is functions of 2 or more real variables. Basically, we'll do 2 variables or 3 variables, but most of the time we will be dealing with problems which after formulation will boil down to 1 variable. Okay, but the idea is our first attack on several variables. We will mainly work in the plane or in R3, in 3 space, but the techniques we develop can be generalized to n-dimensional space, but that is not done in this course. That if you are interested, in second year math course, there's advanced calculus. That's where you take higher dimensional applications of derivatives and integrals. Okay, so what shall we do in this class, in this calculus? So let me go over this quickly. Okay, before the technical stuff, let's look at the logistics of the course. So, okay, so in the first class. Okay, so you'll see that we will have 2 midterms with the percentages 26, 2 over 3. Don't worry about those. Excel calculates these, so don't worry about them. The final exam will be announced by the university later on, so we don't announce it now. There will be quizzes, lots of quizzes, and the lowest grade of your quizzes will be dropped and the others will be average. If you don't attend the quiz, that's considered 0, so it will be dropped. There are unfortunately no makeups for quizzes because quizzes are supposed to be classwork. I will tell you when we are going to have quiz, but officially quizzes are surprise quizzes, so that's why there are no makeups for this. There will be several homeworks on WebAssign. You must register to WebAssign. For this, how to sign up on WebAssign is given on Moodle. The official page for this course is the Moodle page. Okay, so you have to follow Moodle. It is your responsibility to read everything on Moodle because all official announcements are made there. Once it is posted on Moodle, it is assumed that you read it, understood it, and now it is your responsibility. In order to register to this course on WebAssign, you must use this course class key for this course. It is somewhere here. Since you already have a WebAssign account from last semester, you will register to this course. So you are already registered to WebAssign. You have to register to this course separately. Again, there will be several homeworks. The lowest homework grade will be dropped. The others will be average, and that will correspond to 10%. So course schedule is here, Monday and Thursday, as you know. Okay, so I think these are the only non-mathematical things. Okay, another thing is in all classes we have attendance. Attendance does not affect your grades in any way, but we do this for statistical purposes first, and second, there are times when we have to answer if a student is alive or not. So we check if the student is not coming for a month, then there's a reason for alarm. Okay, so other than that, there is no reason for this attendance. So I want you to sign your name once every time you come to class. On Monday you sign once, on Thursday you sign once, even though we take 2 hours. So we are just checking if you are alive or not. Okay, so don't sign for your friend's place, just sign your own. Okay, so I'll pass it here. Okay, so we have the syllabus. I'll talk about the syllabus in a minute. I mentioned Moodle, I mentioned attendance, WebAssign. Okay, so these are the non-technical things. Okay, so let's quickly go over what we will do. Now this week we will do a review of analytic geometry, but we will only do those parts which are used in the syllabus in calculus. We will be interested in tangent lines, tangent planes, integration on a surface, etc. So we will only do vectors, lines, and planes. Given 2 planes, how to find the perpendicular to that, how to write the equation of a plane, how to write equations for lines, etc. So we'll be interested in these. So this week we will slowly go over this. Then start the main part, partial derivatives. So last semester we did derivatives. So if you have a function of x, you take the derivative. So we assume that you all know that. If there are several variables, you take derivatives one by one. But there is a theory behind this. There are some fine points, and we will do that. The highlight of this section will be finding minima and maxima of functions of two variables. Of course, there are ways of finding minima and maxima of functions of more than two variables, but the procedure is long. So the only thing that you can do by hand is the two variable case. So we'll show you how you find the minima and maxima of functions of two variables. So that will be the highlight. Then we'll pass to multiple integrals. We'll explain the meaning of multiple integral, which is very complicated. You cannot calculate it. Fortunately, there is a theorem called Frobenius theorem. Frobenius theorem says that you can break it up and calculate it in the way you know how to calculate. You calculate integrals one by one. If there are several variables, you integrate respect to each variable one by one in a certain way. So we'll teach that certain way. So that's the multiple integral part. And then comes probably the most interesting part, infinite series. You want to add infinitely many things. This starts from 2000 years ago. You add 1 plus 1 over 2 plus half of that plus half of what you added before, and everything adds up to 2. So how is this possible? Okay, so at first it doesn't look like this has anything to do with derivatives or calculus, but surprisingly, to check if an infinite sum actually adds up to a finite number or not requires techniques of calculus. Not necessarily derivatives, but limit operations and epsilon delta calculations. So I will teach the limit operations, the techniques. And of course, the way eventually in the last few weeks we'll tie it to calculus. Given a function, it can be approximated by a polynomial. You can increase the degree of the polynomial. It approximates it better. So if the degree of the polynomial goes to infinite, now you have infinite sums. Okay, a polynomial is x to the some power times something plus again x to the power something else times some number. If you have infinitely many of these, now that's called a power series, and the function can be exactly equal to this infinite sum. Okay, and this helps us to calculate precisely the value of a function. Well, precisely here means that, of course, in everyday life you don't want precisely. Who uses pi with the exact value? If you are doing astronomy, pi is 3 for you. If you are doing other everyday lives, pi is 3.14. That you can do almost every calculation with that. So with these infinite series, depending on what kind of accuracy you want, you can calculate that. This was very revolutionary at the time because in navigation, if you are interested in this, eventually everything boils down to finding the value of sine of 1 degree. If you can calculate the value of sine of 1 degree with little error, then from there you can do lots of navigational calculations. And before Newton's or Leibniz techniques came, that was only approximate. And now we will show that you can calculate this to any degree of precision. You say, I want to calculate sine of 1 degree so that the error even though I don't know exactly what the value is, the error I want to make must be less than, say, 1 over 1 million. Okay, so you add so many terms, and that's the value. And now you are assured, the general theory will assure you that the error you make is less than 1 over 1 million. Okay, if you don't like 1 over 1 million, make it 1 over 100 million. Okay, then you add a few more terms. Okay, so that was the revolutionary idea at that time. Nowadays, there are better techniques. Better means faster techniques to calculate the values of these transcendental functions. So in your calculators, etc., those other techniques are used, but this is the beginning of the theory. Okay, so this also explains why the other techniques work. So this is what we are going to do this semester. So The only advice is that you should read the book, okay? Every day after class, you should ideally spend, if you spend 2 hours here, ideally you should spend 4 hours that day to go over this, okay? If you are lazy, spend 2 hours after class on this thing, but you should read the book, you should go over the exercise, you should go over the examples. Looking at the examples, you must attempt all the exercise at the end of the section. Okay, so the idea here is not to solve all these things. The idea is to understand and to be able to solve it. There are 2 aspects of learning mathematics. First, the general theory, whether you understand it or not. And the second part is, can you apply it? Can you really do it? Okay, so the example is always like riding a bicycle. Okay, I can teach you the theory of riding a bicycle in 1 sentence. Okay, first of all, you must roll. Okay, if you stand still, you fall. When you are rolling, if you are falling to the right, you turn to the right. If you are falling to the left, you turn to the left. Okay, so this is the theory. There is no other technique in riding a bicycle. Okay, so you understand this, but then you hop on the first time you hop on a bicycle is when you take your first midterm, you fall down. Okay, so you should first understand the general idea behind calculus and then solve these problems. Show yourself that you can apply your understanding in actually getting numerical answers, and then you take the final exam. Okay, so the exam will be trivial for you. Okay, so the kind of problems you see in the exam must be so that when you see the exam question, you should be able to say yourself, "Oh, I solved a similar problem before." If the exam question is new to you, okay, you are dead. Okay, so this is how calculus works. You have to devote some time to it. And just look at it this way. You will devote this time only this semester. Okay, so then you will learn it. It's just like riding a bicycle. Once you learn it, you don't forget it. Okay, so that is the thing. And there is this tiny thing here, the final deal. This final deal says that if your first midterm is accidentally low, you should not quit the class. You should continue, because then if your second midterm and if your final midterm are higher, your lower midterm will be replaced with something slightly better. Okay, but you see, if you study this formula here, if your first midterm is 0, then this final deal will again give you 0. Okay, if your first midterm is 10 and your other grades are higher, then that 10 will be 20. Okay, so it doesn't help much. But if it is 35, 40, then you get higher grades, then that 35 can go up to 70. Okay, so that helps you. Okay, so this is only to prevent some accidents on your part. But scoring 10 or 20 is not an accident. That's your fault. Okay, so these are the logistics of the course. So let's see. I'll follow the book. So when you go home, you should also read and follow the book. So let's see. Let's start from chapter 3. Okay, so let's see. Now, okay, so this is calculus 2. Okay, so we will start with we will study mostly functions of 2 or 3 variables. Okay. Our techniques work for more variables, but we will not enter into that. Okay, so the reason why we study only 2 or 3 variables while our techniques work for 30 variables is because in calculus we want to draw pictures so that we get a geometric intuition of what's happening. then when it comes to working with 7 parameters, so you know that there is some 7-dimensional space which locally looks like something similar what you have learned. Okay, then you say, okay, even though we had 3-dimensional space, even though we had pictures, we didn't rely on the pictures. There was a technique of calculating things. So if it is now 7 variables, who cares? I'll just use the same techniques, okay? To initiate you to this state of mind, we only do in 2 or 3 variables. Okay, so here we can draw pictures. Okay, so 2 variables. So this is generally plane, and 3 variables. So this is generally space, 3 space. Okay. So when we do this, first we will be interested in vectors. Okay, so let's start with vectors in R3. Okay, so everybody has an idea of a vector, so let me go over this. In R3 we have coordinates. This is how we draw the coordinates most of the time. X, Y, Z. Okay, so this orientation of X, Y, Z coordinates is standard and is called the right-hand system. Okay, so if you consider your right-hand system, so your fingers go from X to Y, and your thumb points in the Z direction. Okay, so that's what this is considered. So this direction is the standard direction, standard orientation. That's counterclockwise. So the other way is clockwise. So this direction works nicely in mathematics. So that's why in physics we always choose this direction. Why we call it counterclockwise? Why didn't we change the order of clocks? Okay, so if you look at your clocks, it turns this way. But this is, why is it going in this way? Because if you look at sundials in the north hemisphere, the shadow turns like this. Okay, of course, it doesn't go 180. It doesn't go 380 degrees because it turns only. You see it only. You observe the shadow only in the daylight, and it turns this way. So it is clockwise. That's the standard clockwise. So now when we are mentioning this, when this is standard, so we have to call it counterclockwise. Okay, so these techniques are mostly developed or written in the northern hemisphere. So when you say clockwise, it's the clockwise of the northern hemisphere. In southern hemisphere, this is the clock direction, but again, in mathematics, this is called counterclockwise. Okay, so that's the system. Now, a vector. Okay, so let us look at coordinates. A point in R3 is given by coordinates. So from coordinates we are trying to get, so suppose this is the point P. Okay, so it has coordinates, say x1, x2, x3. Okay, so P is given by coordinates. Okay, so these are numbers. x1, x2, x3 are real numbers. Okay, so in calculus we will be dealing only with the real numbers. Later on, next year, you will see that we also work on complex numbers. In complex numbers, instead of R3, you have C3, but then you don't have arrows like this because C is actually a plane. So C3 will actually be a 6-dimensional real space. You don't have any pictures. So that's why in this course we try to look at the algebraic mechanism of dealing with higher dimensional spaces, so that when you come to complex numbers C3, C5, you know that, okay, something is going on there, but this is how you handle them. Okay, so a point is given like this. A point is also considered as a vector, is also considered as a vector starting from origin, vector from origin to point P. Okay, so we denote it like this. Okay, so and sometimes we denote it like this. Okay, so these are notation. You can also use this as a vector. So a point can also be seen as a vector. Okay, so there is nothing new here, but the interesting thing is the following. So let me do this. So sometimes we have two vectors, say P and Q. Okay, so suppose this is the picture. So here is, say, P, here is Q, and we consider their difference. Okay, say Q minus P. Okay, so say Q minus P. Okay, and we draw it like this. Q minus P. So how do you know whether you put the arrow here or not, or here? It's easy. You just follow the arrows. Okay, so you go like this, you end up Q. So then you add this, and you check if you also get Q. Okay, so if you go like this and you can't go like this, so it's not working. So just to add these things and get Q, it means that you put the arrow correctly. Okay, so let's say P is, as we said, x1, x2, x3. Q is, okay, let's be scientific. Let's say x1 prime, x2 prime, x3 prime. Then Q minus P, as we all know, it will just subtract these things, x1 prime minus x1, x2 prime minus x2, x3 prime minus x3. Okay, so but you see that this is now a point. Okay, so it's a point somewhere here. Okay, so if you look at this thing, this point is Q minus P. If you put these coordinates here, it's somewhere here. Okay, so this is the only thing that you should keep in mind when you are working with points and vectors. Geometrically, we like to draw vectors wherever we want them, wherever it geometrically or physically makes sense. But in the calculations, all vectors are like this. All vectors start from the origin. Okay, so this is a point or a vector from the origin. Okay, so all vectors, wherever you draw them, are represented by vectors. Okay, the technical word is emanating, starting from, coming out of, from the origin. Okay, so that's the algebra of these things. You have to remember that every vector is actually a point. Okay, so in some books, well, mostly in calculus, in the exams, always you will use a different notation. Okay, another notation for vectors in R3. Okay, so the vector 1, 0, 0 is denoted by I. Sometimes it is denoted by I with a vector with an arrow on it, and sometimes in the book it will be a boldface I. So this is generally in the book. Okay. So later on, when you do linear algebra, sometimes this will be called E1. Okay, so this is for linear algebra. When you take the linear algebra course next semester. Okay, so then you see the next thing is 1, 0. This is J, and the same thing here. It is then, next year it will be called E2, but for us it will be J, and this one, 0, 0, 1 is K. Okay, so this is only for R3. In R4, we don't have such a notation. In R4, then you have to use either these things or you have to continue with using coordinates. Okay, so this is when we are doing, since in Calculus 2 we will be restricted only to R2 and R3, it helps to use these things. With these notations, for example, if you have x1, x2, x3, we write this as x1i plus x2j plus x3k. Okay, so most of the time, I believe also in the exams you will see vectors written like this. Okay, so I prefer to use it this way, but this is a personal taste. Okay, some people prefer to use it this way, some people use it this way. The important thing is to know that they are the same. You should be able to shift from one to the other without thinking. Okay, so this is what we have for coordinate system. Okay, we will be using some simple descriptions. Okay, so let me erase this. Okay, so we will be restricting our attention to some regions of R3. Okay, so we will describe, so we need to find ways of describing these regions algebraically, let's say. Okay, so the reason why we want to do these things algebraically is because in the figures we can fool each other. There are books in high school, maybe you find them wrong proofs using figures. Okay, so you can prove lots of funny results about triangles by drawing pictures. Okay, but if you correctly draw those pictures, for example, you look at certain lines. Actually, if you draw them the way they are described, they will intersect at some point outside the triangle. But if you draw them inside the triangle, then by showing that certain angles are equal, something is less than the other, you can prove anything you like. Okay, but then by looking at the picture, you are convinced. There are three lines, they intersect inside the triangle. Okay, nobody suspects. Okay, but you have to, since we have such experiences, okay, those things are carried to these technical books, and we want to write everything technically, algebraically, given equations, so that even if my figure is wrong, you can look at my equations and you draw the correct figure and tell that my figure is wrong. So that's why we don't rely on figures. Figures, if correctly drawn, they give us inspiration about what to do. And sometimes they give us the wrong inspiration, but that's science. Okay, you have to try and make errors. You make 100 errors, nobody cares. And at the end, if you do one thing correct, okay, so that's registered. That's doing science. Okay, so for example, the easiest way, so we will do several of these things as we go along. The easiest ones the easiest ones are like this. Say, for example, the plane, well, we don't know at this the set which is defined, which is defined as let's say x equals 2. Okay, so let me go over this once. Okay, so this means we consider, well, this is in R3. Since in calculus we are working mostly in R3. This means we are considering a set, the set of points x, y, z in R3. Okay, so remember that this means belongs to, or we read it as in. Okay, so it's something we used last semester, such that x equals 2, no conditions on y and z are given. So we say y and z are free. So that is, we consider all points in R3 of the form 2, x is 2, y and z are free. Okay, this is a trivial example, but change this to a more complicated expression. This is how you think about this. Okay, so we are looking at all points x, y, z in R3 which satisfy this condition. Here in this example, I deliberately chose a totally trivial example so that you see what goes on through our mind. If I write a complicated example here, then the example overshadows the method of thinking. But the method of thinking doesn't change. Okay, so we can, if this expression is simple, sometimes we can draw pictures of this. In general, if you write an arbitrary expression there, it requires some theory to draw the pictures. You cannot just put it in the computer and get an answer. Okay, so for example, in this case, let us use the usual thing. So x, y, z here. So this is x, this is y, this is z. So on the x part, I'll take 2. Okay, this point is here. If I consider this line, all the points here have x equals 2. And I consider this, again, all the points here are, so a point here is of the form 2, y, 0. A point here is of the form 2, 0, z. Okay, so consider this plane. So I'm doing this only in the first quadrant. See, we are not too ambitious to see all of the R3 at once. We generally try to see what is happening on the first, well, this is not quadrant, this is octant, right? The first octant. So I consider a wall here, and a wall here. I only try to understand what's happening here. If it doesn't help, then I try to forget this wall and see where it goes. Okay, so now we have this plane. Any point on this plane is of the form 2x, y. Okay, so this plane is the set that is described by this thing. Okay, so for simple examples, if I draw this picture correctly, now everybody understands this. But for more complicated things, we need an expression here. Okay, so, well, for another thing is given by, instead of this, a square is given, a circle is given. So let me also go over that once before we come to more serious things. Okay. So such things are going to be used very often. So that's why I'm going this. Another example. The surface x squared plus y squared equals 1 in R3. The way we think about this is in R3 we have 3 variables. only two of the variables are bound to each other by a condition. So this means immediately that z is free. Okay, if you find x squared plus y squared equals 1 in the plane, in the xy plane, then on top of this, any z coordinate point will satisfy this. Okay, so this we will be using such expressions very often. So what happens again here is in the xy plane. Okay, so this is x squared plus y squared equals 1 in the plane. Okay, then I consider these points. So any point here is of the form x, y, z with x squared plus y squared equals 1. Okay, so no condition on z. So this goes up to infinity, and also down it goes to infinity. Obviously, it turns around the z-axis, but I'm drawing only what I see in the first octant. Okay, so again, we have the usual distance formula that we use in the plane. In the space, we again have the same thing. The distance formula in space is, let's say, the same, not exactly the same, but the idea is the same as that of the plane. Okay, so first of all, the length of a vector let's say P. P will be given by x1, x2, x3. So we denote this like this. This is the absolute value sign. We use it because the length of a vector in one dimension is its absolute value. Okay, in last semester we only had the x-axis. On the x-axis, a number can be considered as a vector from the origin up to that number. Okay, and it has a length. Its length is given by absolute value because if it goes the wrong way, again, it has a certain length. The sign is a different property. So since the idea is the same, in higher dimensions, we use this. In some books, there will be two lines here, but we will not use it. So this is the positive square root. So let me emphasize that we take the positive square root of x1 squared plus x2 squared plus x3 squared. Okay. So given two vectors, or let me say given another vector, just to save some ink. Given another vector q. Okay, let's say this time y1, y2, y3. These are numbers. The distance between them is the length of p minus q. Or you can write it as q minus p. Okay, and that thing is again positive square root of x1 minus y1 square, x2 minus y2 square, x3 minus y3 square. Okay, so this is the same thing. So you see, in one dimension, you have this square root of square is just the absolute value of what you see there. Okay, so x1 minus y1 absolute value is the distance between the points x1 and x2. In two dimensions, we have this, and this follows from Pythagoras' theorem. In three dimension, again, if you draw this picture, it will follow from two applications of Pythagoras' theorem. But now you get the idea. In Rn, a point, the length of a point is again will be given like this. Okay, and the distance between 2 points in Rn will be given like this, but you have to continue using all the coordinates. Okay, so the idea is the same. Okay, so using this, for example, we can write the equation of a sphere. So maybe I should skip that. Everybody knows the equation of a sphere. Or maybe just to remind you from high school that the center and the radius appear in the equation. So let me write this in half a minute. Okay. Example. Equation of a sphere. Now a sphere is given by its radius, and well, normally if we are just talking about a sphere is well defined by its radius. Only one information is enough. But if we are going to locate this sphere in R3 somewhere, so we have to tell where we are putting it. The general thing is, of course, to tell where you put the center of this sphere. Okay, so we need two information, two pieces of information to describe a sphere in R3. So it's again the same thing as the kind of information we need to describe a circle in R2. You have to give the radius and where the center is. So center. Generally, we use subscript 0 to emphasize that the point is fixed. Okay, so that's just a convention. Radius. Okay, so this is again another strange thing, that somehow in the history of mathematics from diameter we shifted to radius. And if you read well, you can't read it, but if you look at popular books on old-time mathematics, all of these calculations are on the circle is given by diameter. And suddenly somewhere people started to talk about radius. Okay, so now we are using radius. Maybe 100 years from now on you'll use something else. Okay, so equation. So we are talking about the set of all points whose distance from this point is equal to r. Okay, so we know the distance equation. So we will say that r is equal to square root of this thing. But nobody likes to work with the square roots, because in calculus we always take derivatives. When you take derivative, this square goes down in the denominator. And then what do you do with the derivative? Most of the time we are interested whether the derivative is 0 or not. So the denominator does not give you any information about whether it is 0 or not. We are always interested in what is above. And what is above is the derivative of inside. Okay, so in calculus, we are interested only the information that this inside gives us. So that's why whenever it is possible, we square things. Okay, so the equation will be the distance is x minus x sub 0 square, y minus y sub 0 square, plus z minus z sub 0 square is r square. Okay, so that's again the same thing. So now you can talk about unit sphere, which is very important in doing lots of mathematical calculations. Then unit square is when r is equal to 1. Then you will hear stories about unit spheres in Rn. How do you calculate the volume of unit sphere in Rn? Its volume involves gamma function, etc. Okay, so these things become interesting, but then again the formula is the same. If you have 35 parameters, you will have 35 expressions on this side, and that's equal to radius square. Okay, so these are the things. Okay, before we pass to dot product, okay, so before we pass to dot product, in 5 minutes, let me remind you what we do with vectors. Okay, so it's time to erase this, I think. Okay, so these things are generally called yoga of vectors. Okay, so if you say A, okay, let's say A and B are
vectors. So these are in R2 or in R3. Okay, and C is a real number. Then say A is equal to A1, A2, A3. B is B1, B2, B3. Okay, then we have the usual things from high school. So this is the vector CA1 plus CA2, CA3. And A plus B is A1 plus B1, A2 plus B2, A3 plus B3. Of course, you can have minus here, then those minuses will go there. And notice that this is the same as B plus A, because here we are just adding numbers. So what else do we want to remember from high school? Let me check. Okay, the multiplication. This is called multiplication by a scalar. So that's probably the only thing that we have to learn. Multiplication by a scalar. Scalar means the constant that you are using. Here we are using real numbers. Next semester when you use complex numbers, your scalars will be complex numbers. Later on if you use quaternions, etc. So scalar is a neutral word saying that this is the constant in your working field. Okay? So we are here using real numbers. Multiplication by a scalar distributes over addition. So this is CA plus CB. So let me check if that's all we want to remember. Okay, so I think these are enough. The other things are more obvious than these things. Okay, let's take a break, and next hour I'll start talking about dot product.